Final lesson and video of the year in terms of new material as we move into chapter 12, and we only have to cover one section in chapter 12, which is really confidence intervals and inference testing for regression. So this first part in here, and you'll see I'm going to skip a lot of stuff in here because a lot of it is kind of abstract and not really necessary for what we're doing, but I will kind of give you the overview of what we're talking about here. So when we're talking about regression, remember, we are creating a regression model based off of our sample data to try and estimate or make predictions. So what is the difference between a sample regression line and the true population regression line? So think about if we wanted to compare height and weight, and we took a simple random sample of 20 Middletown South seniors, and we created a regression line based on those 20 seniors. That would be a sample regression line. If we looked at every single student at South, or every single senior at South, and we created the regression line for everybody, that would be the population regression line. Notice that there's no y hat anymore, it's just y. And then our a changed to a lowercase alpha, and our b for the slope changed for a capital letter beta. This next part, not overly important. It's talking about the sampling distribution of b, the slope. What shape, center, and spread does it have? It's approximately normal. The mean of all of your little sample slopes is equal to the population mean, and then there is your standard deviation of the slope. So what this is showing you is, okay, say everybody went out and they took a sample of size 20 and everybody created their own little regression lines. This is a sampling distribution of the slopes of those regression lines of everybody's individual samples. You have some hypotheses that I've written here that would correspond with that. And that would be that B, your slope is equal to 0, meaning that there's no association. Remember, 0 slope would be a horizontal line. And then your alternative would be B is not equal to 0, meaning that the slope is not equal to 0, and there is some association between your variables. So that kind of gives you an overview of the foundation of this section. You don't have to worry about this stuff in here or this stuff in here, as well as the conditions for regression that are for inference here. There are 5. The scatter plot of x and y appears linear. The observations must be independent. You want to graph the residuals. You need equal variance in your residual plot and a random sample. Not overly important that we're focused on any of this, but if you want to put that in your notes, feel free. We're skipping down in here to the bottom of the page, which is important. And that is the formula for constructing a confidence interval for the slope. Everything in this section is related to inference, related to regression is all based on the slope. So what is the formula? The formula is, like every confidence interval, statistic plus or minus the critical value times the standard error. Your statistic is your sample slope. Your t critical value, you're going to get from the t distribution table, which we can get from our formula sheet. And then the standard error, you're going to get from your computer output, okay? The t critical value is not from the computer output. All of these problems are going to be using the computer output that we saw in the last section. It is from the table in your formula sheet. And one key thing for slope is that your degrees of freedom is n minus 2, which is different from what we saw for chi-squared or for mean when it was n minus 1 or number of categories minus 1. For slope, your degrees of freedom is n minus 2, your sample size minus 2. And we're going to be getting our critical values by going to the t critical value table, or our t distribution. We'll go to whatever confidence level we need, and then degrees of freedom of n minus 2. So based off of this. Remember, the infinity row is only used for z critical values for proportions. So if we look at this problem here, a lot of this is going to be based off using that computer output here. So if we want to construct a 99% confidence interval for the slope, we'll be using our slope, which is here. Remember the constant, that's the y-intercept, standard deviation of the residuals, r squared. Here's my slope. So for my formula, I need the slope and I need the standard error. So the stuff that we were ignoring before is now coming into play. And the standard error for the slope is right next to the slope at 1.943. So now we have the slope and now we have the standard error. We need to find our t critical value. So if we look here, it says they randomly selected 12 carnations. So my degrees of freedom is going to be 12 minus 2 is going to be 10. So to get that t critical value, we're going to go to our table B, t distribution. We're constructing a 99% confidence interval. So we're going to be in this column in here. And if my sample size was 12, the degrees of freedom are going to be 10. So my t critical value is going to be 3.169. Okay? So there's my critical value right there. You can assume the conditions are met. This is going through the process, which we will go through in class on how to do this. 15.2 plus or minus 3.169 times the standard error, and you'll get your confidence interval there. We are 99% confident that the interval from 9.04 to 21.36 captures Z, and this is a confidence interval for the true slope of the regression line, that in this case is relating hours of freshness to amount of sugar. And again, we will go through this example a little bit more in depth in class, but at least you have the foundation for it. Can you use the calculator to do the do step? You can, but it's not worth it. Almost always when you're given a problem like this, you'll be given the computer output. If you're given data, you'll need to enter that data into the calculator under stat and edit. And then if you go to stat and over to test, notice F is a linear regression t test, and then G would be your linear regression t interval. You'll need the raw data to do this. If you don't have the raw data, then there's no way to run this test. So L1, L2, confidence level, and then calculate, and it would get you the answer. This is for a different problem. That's why it doesn't match up. Okay, so it's not worth it to do it. And most times you'll be given the computer output. Final thing is a significance test for slope. Again, this formula is not on the formula sheet. Your test statistic is a t test statistic that you'll be doing. To find it by hand, you would take your sample slope minus the population slope, which is assumed to be 0, like we talked about earlier, divided by the standard error. Once again, though, you'll be given a computer output almost always when you're dealing with this type of problem. So here's a scatter plot with time and tip, how much time people spent at the restaurant or buffet and how much they tipped in money. They're giving us a computer output as well as the scatter plot and a residual plot that's based on the z-scores. Or sorry, this is here's the scatter plot. Here's the residual plot. We don't really care about this one here. This is your basic residual plot. So here's my y-intercept, goes with a constant. Your other value is your slope. Here's my standard error of the slope. And then these other two parts that we were ignoring before, this is your test statistic t, and this is your p-value for your significance test for the two-sided test. Okay? So that's for the two-sided not equal to alternative hypothesis. So standard error, slope, y-intercept, test statistic, p-value. There's my standard deviation of the residuals. There's my r squared. We'll do part B in class and C, but I want to talk about the significance test. And again, we'll go through this in class more in depth. Charlotte's question is that people who spent more time tended to tip longer. Okay? Do this by convincing evidence that customers who stay longer give larger tips. So my null hypothesis is that the slope is equal to 0. That's always your null. Your alternative here would be that B is greater than 0. A slope greater than 0 means more time is more tip. And this beta represents the slope of the true population regression line. We assume the conditions are met. You're using the computer output. Your test statistic is 1.23. That's given to me in the table right here. This is the p-value for the two-sided test, going in both directions. If we want the p-value for the one-sided test, we need to take that p-value and divide it by 2. So this is the p-value for the two-sided test. To get the one-sided test, take it and divide by 2, and you'll get 0.1235. That 0.1235 is greater than 0.05, so we would fail to reject the null hypothesis. Therefore, we do not have convincing evidence that the true slope is greater than 0, and parties who stay longer leave larger tips. So this is pretty easy in this section because everything is really based off of the computer output and knowing the different parts of that computer output. You'll need to take the standard error as well as the slope when creating the confidence interval. And then you'll need the test statistic and the p-value when running a significance test. That is all for this lesson. We'll talk more about this in class, and I'll see you then.